Hello everyone, welcome to the second hands-on session of the Introduction to Machine Learning course. I am Anirban Santara. I am doing my PhD in machine learning. Today we will learn a couple of cool machine learning algorithms. In the first part of the session we will study how to use K nearest neighbor classification algorithm for classification of flowers of the iris data set, and in the second part we will learn how to use K nearest neighbor classifier along with principal components analysis for face recognition. We will use Python language as our language of choice for programming in this course. scikit-learn is a very popular machine learning library, and it has a lot of machine learning utilities. We will study how to use K nearest neighbor classifier and randomized PCA from scikit-learn in this session. Without further ado, let's jump into the exercises. The first topic for today is K nearest neighbor classifier. The K nearest neighbor algorithm is a non-parametric machine learning algorithm, and it maintains a database of the training samples, and every time a query is made to this algorithm, it looks up the database and it finds the K, which is specified by the user, nearest neighbors of the query point from the database. Now once it has retrieved these K nearest neighbors, it goes and finds out which class is the most predominant among the retrieved neighbors, all right, and the most predominant class is assigned as the target class for the query point. And we will use a modified version of the iris dataset in this exercise. The iris dataset has flowers, and these iris flowers fall in three species, all right, and the task is to classify the iris flowers from the sepal and petal dimensions. For the ease of visualization, we will choose just the first two feature dimensions, that is the sepal dimensions, the sepal length and the sepal width, for describing the iris flowers. The first task is to split the available data into training and test segments. So we randomly choose 75% of the data that is available to us for our training set and save the remaining 25% for the test set. So this part of the code which you see on the screen describes how to do it in code. The next step is to go ahead and make the K nearest neighbor classifier. So for that you have to make an object of the class K neighbors classifier, and you have to set the number of neighbors to a required value. So for example, I have set it equal to 5, and then we do a model.fit xtrain ytrain. So this thing loads the data set into the model and saves it for reference when query is made. The next step is to check out how the algorithm is performing. So we find a query point, and the query point is the first example from the test set. So we get the prediction from the model by using model.predict of the query point, all right, and in this way, so the nearest neighbors module of the scikit-learn.neighbors library helps us to visualize how the algorithm actually works out, all right. So here you can see the query point is the dark blue triangle, and the neighbors have been highlighted in yellow, and we can see that class 2 is the most predominant among the classes of the neighbors, and hence it predicts the class 2 as the class of the query point, all right. And so this is how the nearest neighbor algorithm works, and it is a highly popular algorithm, and it works well when, say, the data set is varying in its number of classes, for example. So you cannot afford to train a parametric machine learning model time and again every time the data changes, or the number of classes that you want to you want your classifier to predict, that changes with time. So the K nearest neighbor algorithm becomes highly relevant in those scenarios. So the next part of the session is about principal components analysis. So, the principal components analysis algorithm is a highly popular algorithm used for dimensionality reduction. Now, dimensionality reduction means reducing the number of variables that we use for representing our data. Now, why does it become relevant in some cases? It becomes highly relevant when we have to deal with high dimensional input spaces. So, a phenomenon called curse of dimensionality happens in such scenarios. So, curse of dimensionality actually refers to a set of problems that crop up when we have too many input dimensions, and these problems crop up just because the volume of the feature space increases at such a high rate as the number of feature dimensions increases, that the amount of data that is available to us becomes sparse in such a high dimensional space, and the amount of training examples that we would need for getting statistically sound results from a machine learning algorithm in such high dimensional vector spaces increases exponentially with the number of dimensions of the input space. So, that is why we would like to reduce the dimensionality of the feature space without losing much information, and the principal components analysis algorithm is one of those algorithms which become highly relevant in this particular scenario. All right. So, the principal components analysis algorithm, it looks for uncorrelated feature dimensions. All right. So, sometimes what happens is the observations we make, the variables that we observe are highly correlated among themselves. For example, in this diagram you can see that the x and y axis which the observed data originally has are highly correlated, right, and the principal components analysis instead chooses a pair of different directions which are mutually orthogonal to each other, and if we represent the data along like just one of these principal components, the most of the variance of the data is preserved. And the principal components analysis algorithm, it looks for uncorrelated feature dimensions. So, the amount of redundancy that is present within the correlated variables is removed when we transform the data into the space of the principal components, and the principal components happen to be the eigenvectors of the covariance matrix of the data. And let us study the principal components analysis algorithm, how it works and how we can use it to reduce the dimensionality of images of faces and use the reduced dimensional face vectors for face recognition. The general workflow of any face recognition algorithm goes as follows. First, we have a whole database of known faces, and once a new face is presented, we go and make a query to the database. The database returns a set of faces which look the closest to the face in the query, and all of these faces are known. All right. So, the database has known faces, so it outputs the a set of faces which are already known to us and are the closest to the one that has been sent in the query, and then we go ahead and choose the face that is the most similar to the face in the query as our output. So, this is the workflow. Now, how does principal component analysis work, and in this particular scenario we will study in this section of the tutorial. The data set that we will be concerned with is the Olivetti face data set of scikit-learn, and these are faces, grayscale images of faces of 40 people, and each of these 40 people have 10 faces. So, altogether we have 400 faces, and these faces have been cropped to a size of 64 cross 64 pixels. And next we go ahead and make our train and test split, 75% training data, 25% test data, and we use the train test split function of sklearn dot cross validation for doing this exercise. Then we go ahead and find the eigenfaces. So, what are eigenfaces? Eigenfaces are the principal components that we were talking about. The eigenfaces, they are the eigenvectors of the covariance matrix of the data set of faces. So, these eigenfaces are a set of components, a set of vectors you can say, and if a face which can which encode a lot of information about faces. So, a face can be represented as a linear combination of these eigenfaces, and say we have a face of 64 cross 64 dimensions, and that makes 4096 random variables for each pixel of the face. And now these, instead of 4096 random variables which are highly correlated among themselves, we will go ahead and represent the faces in terms of the principal components, and we will be using just 150 of them. Thus, we have done a huge dimensionality reduction. And next, we will see how the principal components analysis algorithm works. So, given a face 64 64, first we go ahead and make a vector out of that. So, we just do a raster scan on the image, and we arrange the pixels along the rows into a vector of 4096 dimensions. And next, we go ahead and find the mean vector and subtract that from the original image. So, the mean face has been calculated by averaging all the faces in the data set, in the training data set, and that is also converted into a vector and subtracted from the image, and thus we have a mean normalized image. This is necessary because it helps in optimization algorithm of any gradient descent based algorithm, all right, down the road. And and it's also necessary for the calculation of the covariance matrix, because the definition of covariance is actually the expected value of x minus mu x times x minus mu x transpose, which has been explained to you in the theory session. And thus, we do this exercise for all the images of the training set, and we have these 4096 dimensional mean normalized images, and thus we go ahead and create a matrix called X, and each column of the matrix is one image from the training set, all right. So, this X is a set of mean normalized training images. Say we have capital N training images, and thus the size of the matrix X will be 4096 cross N. Next, we go ahead and calculate the covariance matrix of the data. So, we multiply X with the transpose of X, and we have R, the covariance matrix. The dimensionality of the covariance matrix is 4096 cross 4096. The principal components will be the eigenvectors of the covariance matrix, and we will see next how to calculate the eigenvectors. So, we will calculate the eigenvectors by using a procedure which is called diagonalization in the context of symmetric matrices, and in general it is called singular value decomposition. So, what does it do? It represents the matrix R as a product of three matrices. The first one is called P, and it consists of the eigenvectors along the columns, all right. The last one is the same matrix transposed, and the central one is a diagonal matrix. Each element along the diagonal is an eigenvalue, and it corresponds to the eigenvector in the matrix P. So, the first column of P is an eigenvector, the eigenvalue of which is the first element of D along the diagonal, all right. So, what we will do is we will just choose the eigenvectors corresponding to the highest magnitude eigenvalues. So, the K, the magnitude of the eigenvalue shows which means how much one particular eigenvector contributes to the to the information, how much information a particular eigenvector carries about the data, all right. So, we choose the k highest eigenvalues and their corresponding eigenvectors, so that so that maximum information is preserved, all right. So, we just choose the first k columns, because these k columns are corresponding to the highest magnitude eigenvalues. So, we should first make sure that the eigenvalues are arranged in decreasing order of their magnitudes, and the corresponding eigenvectors are present in the same same column location as the eigenvalue, all right. So, we just choose the top k eigenvalues and eigenvectors, and this value of k is what we specify to the principal components analysis algorithm, and we specify that to be 150. So now we will do this exercise, this part of the exercise in code. So the randomized PCA algorithm of scikit-learn, it does a efficient implementation of the principal components analysis algorithm. So we first specify that the number of components will be 150, and then we initialize a PCA model, and we say that the number of components is equal to 150, and we fit on the training data. All right. So this does all the operations that we showed before, the entire mean normalization, then the SVD, and then we can just try and visualize the eigenfaces. So the eigenfaces are calculated, the eigenvectors are calculated, they are stored within the model. We can retrieve them as PCA.components underscore. All right, and we reshape them to height width so that we can visualize them well, and we will show them to you in a minute. So once we have identified the principal components, we go ahead and do our dimensionality reduction. So we just preserve the parts that are necessary to us, just the first k principal components. And as you can see that the dimensionality is now 4096 cross k, and we have changed the names to the previous names followed by 1, just to avoid ambiguity. All right. So now we do the dimensionality reduction. So what do? Given an input image, we first mean normalize it. We find the vector, we use the mean image as we calculated before, and we subtract the mean image and we calculate the mean normalized image. Now the mean normalized image is transformed with P1 transpose. All right. We multiply P1 transpose into A, the mean normalized image, and what we have is a k dimensional vector which represents the image in the reduced dimensional space spanned by the top k eigenvectors. All right. So this is how the dimensionality reduction works using PCA, and now we will implement that in the code first. So PCA dot transform of a set of input vectors will do the transformation to the PCA dimensions. All right. So this is what we do here. We transform both the training set and the test set into 150 principal components, and then we do a k nearest neighbor classification of faces in this principal component vector space, in the space spanned by these principal components rather. So what do? We first declare our classifier, we fit it on the training set, and then we do a classification on the test set. All right. And the results are quite nice, quite impressive, and as you can see, some examples of classifications, and we have 55% test accuracy with number of neighbors equal to 5, and we can further tune the number of neighbors and have better and better accuracy. All right. So that was a nice demonstration of how principal components analysis and k nearest neighbor algorithm can come together and solve a very interesting and cool problem like face recognition. All right. So thank you guys. See you in the next video. I enjoyed this time lecturing you. Bye bye.